It's my pleasure to welcome everyone to UL seminar with our speaker, Holger Vömel. Holger got his Vordiplom in physics at the University of Frankfurt, his diploma in physics at the University of Heidelberg. Came here, got a PhD in chemical physics at the University of Colorado. And after his PhD, stayed in Boulder, was a research scientist with both CERES and the PAOS programs at the University of Colorado. Then went back to Germany, working for Deutsche Wetterdienst, running the Lindenberg, at the Lindenberg Meteorological Observatory and running the GRUON, which is the GCOS Reference Upper Air Network, which we'll probably be hearing more about today, I'm not sure. Holger has numerous awards from NASA and NOAA, has over 100 peer-reviewed publications, including 15 first author, pretty impressive, and more than 50 field experiments that he's been involved with, mostly, I think, featuring measurements of the stratosphere and troposphere using ballooning. So with that, I think I'll have Holger take over.
And I hope, yep, that does work.
Actually, it's the most important part. Thrilled to welcome you here as of Monday to work with us in EOL.
Thank you very much. And I'm very thrilled to be here myself. Obviously, I came back for a good reason. Boulder is a very, very nice place, and NCAR is a great place to work. And so I'm really excited to be here. Today, I talk about stratospheric water vapor processes and trends from in-situ observations. And that's really something that traces actually all the way back to my master thesis, where I had the first dabble in stratospheric water vapor. Not successful back then, but after I moved here to Boulder and got involved with the frost point hygrometers, that actually was quite successful, and I'll show you a fair bit about this. Before I start, I want to acknowledge a whole bunch of people. First of all, my colleagues from the Lindenberg Observatory, which I abandoned just a week ago. Tatjana Nebert, Susanne Meyer, Marion Fiedler, Michael Sommer, Ruud Dirksen, Peter Oelsner, Dietmar Daus, and another 9 observers. Lindenberg actually does probably worldwide the most intensive ballooning program of any site. There's 4 times daily radio sound observations, twice monthly water vapor, stratospheric water vapor, weekly ozone, cloud backscatter radio sound, and in comparison, whole shebang. So that actually was a hard part to leave, but Boulder was better. I also want to acknowledge Dale Hurst at NOAA, who took over the balloon program after I left there. Rennie Selkirk at NASA Goddard, who I've worked with, especially in Costa Rica, getting the Costa Rica side going. Jorge Andres Diaz, the local scientist at the University of Costa Rica. And I want to mention Jianjun Bian from the Institute of Atmospheric Physics at the Chinese Academy of Sciences, and Jiangdong Sheng at the Chinese Academy of Meteorological Sciences. I'll show a few of the data we got in the Tibetan Plateau together with these 2 colleagues. So just to give you a little outline of where this talk is going to go. First, a little bit of motivation. Why do we actually care about stratospheric water vapor? And then the how and the where. So how do we measure it, and where do we measure it? So what's the kind of a little background. And then I'm going to look a little bit at the trends. You know, hopefully, that Boulder is the only long-term site for stratospheric water vapor trends, come up to 35 years, but meanwhile, there's a few other sites, and in particular, Lindenberg. So I'm going to show you the results from Lindenberg and compare to some of the other sites. As soon as you talk about trends, you actually have to think about measurement uncertainties. And that's a very important thing. You can't understand trends if you don't understand the uncertainties of your measurements. So I'll say a few words about that one. That also is important when you talk about relative humidity at the tropopause. Stratospheric water vapor is directly linked to what happens at the tropical tropopause. So that's why we actually need to look at water vapor and relative humidity in particular at the tropical tropopause. Therefore, a special section about that one, first in the mid-latitudes and the tropics, and as I mentioned, in the Tibetan Plateau as well. So why is stratospheric water vapor important at all? Why do we care? There's just a few ppm of water, and that's not much, hardly any clouds. Why is it important? Well, first of all, it changes. The Boulder record has nicely shown that. There is variability, but the IPCC report concludes that because of the large variability and relatively short time series, confidence in long-term stratospheric water vapor trends is low. And anybody who knows about water vapor trends in the stratosphere, there's different disagreements between different instruments, satellites, aircraft, balloons. All of this contributes to that, so it remains a big challenge. In the upper troposphere, similar issue, the absence of a homogenized data set across multiple satellite platforms presents some difficulty in documenting coherent trends from these records of upper tropospheric humidity. So upper troposphere and stratosphere, because of the tropopause, is tightly linked. We don't know much about the trends in this altitude region. So here's a paper that Dale Hurst wrote a few years ago from the Boulder record. So that's a reanalysis or yet another analysis of the Boulder water vapor trend. You see water vapor mixing ratio in 2-kilometer altitudes, color-coded are the different layers. And the most interesting part actually is that throughout the 80s and 90s all the way up to 2000, it looked like, well, it's largely going up with some wiggles up and down. But then a very interesting thing happened in 2000. There was a very sharp drop, which surprised a lot of people. And by now we have a little bit of an explanation, but still a surprise. And the last, between 2005 to 2010, a slight increase again. And I'm going to show you the continuation of that record. That's just one site, and actually the only long-term site there is. So it changes. Well, Susan Solomon actually looked at what does this change in stratospheric water vapor do to our climate. Actually, Piers Forster and Greg Shine, maybe 10 years earlier, did a similar study. And she tried to estimate, well, what impact does that have? So here's the global warming from models due to greenhouse gases and aerosols in 80s, 90s, thousands. So what is that? 0.15 more or less Kelvin per decade increase. If you include this drop of stratospheric water vapor in 2001, that estimate actually drops by about 25%. So that drop in stratospheric water vapor has an impact on the tropospheric temperature. And if you include this increasing water vapor trend throughout the 80s and 90s, actually it increases a fair bit again. So stratospheric water vapor does have a significant impact on global temperature in the troposphere. That's why we need to care, that's why we need to measure it, that's why we need to understand stratospheric water vapor. Well, how is it controlled? And that goes back to the very old study by Alan Brewer back in the late 40s. Dobson was involved in that one, and here that's the seminal picture of the Brewer-Dobson circulation in 1949, where he concluded that all the air in the stratosphere has to enter through the tropical tropopause because only the tropical tropopause is cold enough to dry the air to the amount that you see in the stratosphere. And interesting enough, these measurements were done here in mid-latitudes in England with some research aircraft where they first tried the frost point concept on an aircraft. So this is actually based on frost point measurements in mid-latitudes. Classic picture, and that basic picture still holds with some refinements, of course. And one of the big refinements was the work by Jim Holton and co-workers, Peter Haynes, McIntyre as well. But the basic we're able to explain, well, what drives that Brewer-Dobson circulation? And so the main driver is actually here the wave-driven extratropical pump, where wave breaking drives that circulation, leads to large-scale ascent in the tropics, large-scale descent in high latitudes. So if we look at stratospheric water vapor, we should see here relatively consistent trends in this region. Tropics is probably a little bit different. There's also the tropical pipe in there. And then you have the descending branch here in high latitudes. So if you want to measure it, you actually should measure it more than one location, not just in mid-latitudes, Boulder, somewhere here in that range. You should look at some additional sites, and that's what we're going to do. Also very important to notice, this is just a mean picture. So the tropics here is actually symbolized by deep convection going all the way to the tropopause. Meanwhile, that's a little bit refined. So there's the tropical tropopause layer Most of the convection actually doesn't make it up that high. And so this is a refinement that I came up with, or that actually a whole bunch of others, but this is looking at from water vapor observations in the tropics, Eastern Pacific, Western Pacific, comparing. And there are some regions where you have deep convection, sometimes actually going all the way up to the tropical tropopause, but most of them in this detrainment layer are significantly below the tropopause. You also have regions where you have large-scale subsidence, where you have no convection at all, yet you have dehydration at the tropical tropopause. And other regions where you have nothing, where nothing happens at the tropopause. So if you want to understand the mean behavior of the tropical tropopause, you need to look at different regions. Not just take it as a mean picture, but look at the processes in different regions. So if we want to improve our confidence in the trends of stratospheric water vapor, we have to identify and quantify the regions contributing to the stratospheric dehydration. And we have to quantify the importance of the different dehydration processes. Convective dehydration, slow-scale dehydration, wave-driven dehydration, and most importantly, what are the clouds doing? Dehydration always assumes the air is saturated at the temperature you measure, and all the water vapor falls out. But there is things like supersaturation, there's ice particles in the clouds, so this also needs to be studied a fair bit, and that's non-trivial. And since we're looking about trends, another challenge is to increase the reliability of water vapor observations. As I mentioned, there have been a number of disagreements in the past, and we have to overcome those. And we have to increase the number of observations, which is a big challenge today, in particular, given that there is no new satellite project on the horizon for stratospheric water vapor measurements. Nevertheless, important, we have to validate those satellite observations that exist because they give us the global picture. And we have to provide continuity of observations after the end of the satellite record. MLS, which is the strongest instrument right now, is already living on borrowed time. We hope it runs longer, but once it dies, the stratospheric water vapor record from satellites is going to come to an end. So let's look at the vertical distribution. For those not most familiar with stratospheric water vapor, here's just 3 sample profiles to show you the difference. Blue is a polar profile, green is a mid-latitude profile, red is a tropical profile. In a stratosphere, it's largely constant. You have a decrease of almost 4 to 5 orders of magnitude from the surface to the stratosphere, so a very large dynamic range in the stratosphere. And you have this region where there's a transition. That's why I actually didn't separate it clearly. There's a region where you have some stratospheric influence and some tropospheric influence, so here a little bit indicated as this transition region. And interestingly enough, you see here the vertical structure in the tropics, the Chapik quarter. I'll come back to that when I show the Costa Rica data. Well, what measurement systems are actually capable of measuring up there? So here I plotted a whole bunch of measurement systems that measure water vapor at all. So here we have radiosonde, 2 radiosondes. The left one, I separated out the Weisler radiosonde because technological, that actually is the most advanced and best operational radiosonde. Other radiosondes do not get quite as high, so this bar always indicates roughly how high you can measure with that system. Tropics, mid-latitudes, polar regions. So most other radiosondes don't go quite as high, and there are some that are even worse than this. The cryogenic frost point hygrometer, I'm going to show you a fair bit, is currently the only instrument that measures from the surface all the way to the middle stratosphere. So continuous profile. Then we have microwave profiling instruments, this lower troposphere, LiDARs, depending on how powerful those instruments are, maybe get up to the tropopause. I don't know if any of that does it in the tropics. Go that high. Nadir-looking infrared instruments from satellite, microwave instruments from satellites also give you just troposphere, maybe not the tropopause region. Commercial aircraft are slowly coming in. Again, they only go to ceiling altitude of the commercial aircraft. So the only one that's left is research aircraft, WB-52, Global Hawk, those kind of things. They actually make it in the tropopause region and across the tropical tropopause. And then the MLS, I pointed that out, which just makes it to the tropopause region. But of course, with satellites, you have the problem that it has this very large vertical averaging, which is not very suitable if you want to look at processes in a very fine layer. I'm going to show you that. So basically, there aren't many systems that measure it. Aircraft, research aircraft, very expensive, campaign-based, and the CFH right now, the only operational instrument that can be used on a routine basis to monitor. And so we have several sites where we do that. Here's one picture of a launch or launch preparation of a CFH, cryogenic frost point hygrometer. Here you actually see the frost point hygrometer, and because it's an expensive instrument, you want to measure additional stuff to get more information. So we always add an ozone sound to it. There's a radio sound to transmit the data down and give you pressure and temperature. Here's actually a second radio sound on this particular payload. And what you don't see is on this particular soundings, we have 3 more radio sounds on there because we use these particular soundings to compare and evaluate other radio sounds, operational radio sounds. But it's not the focus here. So there you see one of those launches. They're very labor intensive, they're very expensive. You can't do them too often, but nevertheless, you must do them at some sites. So where do we measure stratospheric water vapor? And so here I want to just give you one plot of the GCOS reference upper air network. GCOS reference upper air network, GRUON, is not per se a CFH network. It's actually more a radio sound network to measure not just water vapor, but also temperature and pressure at a number of sites, and that with the best possible quality of observations that you can do. That has been my life in the last 6 years, and I hope I'll continue being involved with that. Remember this acronym GRUON. It actually is an important development going on. Some of those sites measure stratospheric water vapor. That's why I put them up here. Boulder is a certified GRUON site by now. Lindenberg is a certified GRUON site. New Orleans is a certified GRUON site. So Dunkela, about certified. Lauder, again, about certified GRUON site. These sites, GRUON sites, dedicated GRUON sites that also measure stratospheric water vapor. Then we have Hilo, not yet a GRUON site. Costa Rica, not yet a GRUON site. Hopefully will be at some point. And they added here the Tibetan Plateau. There is not a single site in there because there's no monitoring going on. But for the last 5 years, I've been involved in campaign-based observations. And these campaign-based observations have been at almost half a dozen different sites within this region. So that's why I didn't put a single dot in there. But nevertheless, it's a very important data set to look at. So here's just a history of the monitoring operations. Boulder, of course, the longest one since '81. Sodankila, Finland, since 2002. However, only in the last 3 years, they actually do year-round. Before that, they focused on just the polar winter. For the last 3 years, they've done year-round soundings on a once-monthly basis. Lauder got started in 2003. I was actually there to set it up. I started this site here in Costa Rica in 2005 as part of the TCSP program. Lindenberg, 2006. Actually, I visited in 2006 for the first 2 soundings then, but after my move, that's when we really got started in Lindenberg. So since basically 2008, there's routine observations. Hilo, Hawaii, monthly observations since 2010. New Orleans, probably bi-monthly observations since last year. These are the only ones that do routine and hopefully long-term if those sites can maintain the funding. There are many other campaign-based observations, but I exclude them here because climatology is more important than individual campaign-based data. With the exception of the Tibetan Plateau, where we have those campaign-based observations in the last 5 years, and I'm going to show you those at the end. So let's look at climatology and trends. Some of you may have seen a figure like this, some not. I basically took all the Boulder data and actually just from 2008 to 2014 to be able to compare to Lindenberg. This is how the climatology over Boulder looks like, monthly means more or less. What you see here, a nice minimum water vapor in March, April. You see here the seasonal cycle of the tropopause over Boulder, and then relatively flat above that region. If you go to Lindenberg, so Boulder, 40 degrees north, Lindenberg, 52 degrees north, it's almost the same, except here this minimum is a couple of months later. That gives you already a feeling of what is the latitudinal transport time scale. So we see this minimum a couple of months later, and an interesting difference is here in the winter. If I go back, well, you see we have higher water vapor here because we're much closer to the polar vortex and this downwelling branch of the Brewer-Dobson circulation. That you see that in the comparison of those two sites. But what I really want to show you is how do the trends look like at Lindenberg. Color-coded the different altitudes, red 16 to 18 kilometers, all the way to this purple color 26 to 28 kilometer. Water vapor slightly increases with altitude. That's why these lines shift upward with the different altitudes. This is just a straight data as they come, a little bit of smoothing in there. But it's more instructive if I actually take the seasonal cycle out and do the anomaly of these trends for each altitude, because then they just fall on top of each other and it's easier to see what happens. So we see over the last almost 4 years in 2011 as a decrease in water vapor of about half a ppm to 1 ppm, something like that. Half a ppm out of 5 ppm, that's 10% drop. Let's keep that in mind. 10% is very important. Here, before that, the data set is a little bit spottier. There's individual outliers like that. Some of them are directly related to our proximity of the polar vortex, because Lindenberg every once in a while does make it into the polar vortex, or the polar vortex moves that far south that Lindenberg at 52 north is within the Arctic polar vortex in the wintertime. So we get these very high water vapor observations. But we really started with the bi-monthly observations in 2011, and since then the data record has been much more easier to read and easier to interpret. Plus a few instrumental improvements that I implemented there, which again helps to make the data record much cleaner. So if we want to compare this now to Boulder, actually not just Boulder, but the others, 3 other sites. So Lindenberg in dark blue, Boulder, Hilo, Costa Rica. Here I look at the 400 to 440 K altitude. I do this on potential temperature because transport is probably largely isentropic and not on constant altitude. So that's why it's better to look at potential temperature. That's at mid-latitudes, probably the 16 to 18 kilometer region. And you see the nice seasonal cycle of these data. And overall, it looks reasonably consistent. Again, if I do the anomalies, take out the seasonal cycle, this is what you see. Here, again, the data are a little spotty. All the sites had some minor issues, launch frequency, instrumental issues. That's why it's not quite as clean. After 2011, see all the sites here, Lindenberg, Boulder, Hilo, Costa Rica, show this downward. Actually here in the last year, 2013-14, slight increase in water vapor. So what that means, over those 4 sites at this altitude region, they all give a consistent picture. That is a very important statement. There's been recently a Nature paper comparing the Boulder record to a combined HALO MLS data record, where they basically say, well, in the historic records, they're inconsistent with each other. And that's a big thing. Unfortunately, we can't do much with the historic data, neither with the satellites nor with the sondes. So now it's good to see that at least for the last 4 or 5 years, we get very consistent records within the different stations. And that's an important thing. Keep in mind, every dot usually is a different instrument even. So it's a nice piece of work. This is a 24 to 26 kilometer region, 600 to 660 Kelvin. Now you see the big difference between the tropics and mid-latitudes. Tropics, of course, a lot lower because here there's the contribution of methane oxidation not in there yet. You have here, of course, a much stronger contribution of methane oxidation. You also see here at Lindenberg these high excursions compared to Boulder. Again, that's the proximity of the polar vortex, where we make it into the polar vortex and sample very different air. Otherwise, we measure very much the same air as Boulder. Again, if we take out the seasonal cycle and just look at the anomalies, we see here a slight decrease, not quite as strong. There's also a little bit more scatter because there is more variability in this altitude range. So this is maybe 5–8% drop. Keep that in mind, 5 to 8%. So we really need to look at, well, what is the uncertainty of the measurement? Could that be instrumental? Well, a paper I published a few years ago actually looked a little bit in detail. What are the uncertainties of a frost-borne instrument? And that's one of the figures I showed. At the surface, something like 3 to 4% uncertainty, relative uncertainty, goes up in the stratosphere to 9 to 10% uncertainty of the measurements. That's a little bit of a problem. If you want to detect a trend that's less than 10% and the measurement uncertainty is 10%, that really makes you worry. It's like, oh, maybe this is all instrumental. So we really have to look a little closer. Well, what does that instrument do? Where do the uncertainties come from? Here is, that's a schematic of how the frost point hygrometer works. You have a mirror on which you condense a frost layer. And you regulate the temperature of that mirror such that the frost layer remains constant. And the way you regulate the temperature is, first of all, the mirror is always cooled from the backside with a very cold cryogen against which you heat. So you turn your heater off, the mirror gets really cold, and you turn it all the way up, it gets really warm. So this cryogenic principle allows you to measure this very large dynamic range of water vapor, those 5 orders of magnitude, because we can get basically any temperature, frost point temperature, from plus 50 to minus 150 degrees C. So that's extreme. So the way this instrument works, there is a detector and a microcontroller which regulates the temperature. So there's this feedback loop. And whenever the instrument detects a slight change in the frost layer, oh, the frost layer is decreasing. Oh, I'm a little bit too warm, I have to cool. So the mirror gets cooled a little bit. Oh, the frost layer is increasing. Oh, the mirror's too cold, it has to warm up a little bit. So there's this feedback cycle. And this controller that regulates this is the limiting source for that measurement. How well is this thing doing? So here's the uncertainty budget, the total uncertainty budget for the CFH. Controller stability is 0.5 degree. That's how well this thing is doing. There are things like thermistor calibration fit, thermistor calibration reproducibility, I'll show you that, calibration of the reference thermometer, digitizing error, temperature uniformity of the mirror. These are all small things. The limiting factor back then was the controller stability. And so I spent a lot of time actually working on an instrument improving that particular factor, reducing that controller stability. And that's actually how well we can do today. And today, it's almost today, this is not even 2 weeks old, that particular profile that I show you here. But that's actually the last 4 or 5 years that we've been able to do that. You see here just a high resolution profile, and if you can barely make it out, there's a gray shaded area around it. That's a 2 sigma uncertainty to the controller. So it's extremely good. To actually show this a little bit better, here is the uncertainty profile. This is now the uncertainty profile in frost point temperature in Kelvin. So 0.1 to 0.2 Kelvin is the uncertainty of this controller. Now, of course, when you keep in mind, this thing always has this feedback loop. It always has to respond to what the atmosphere is doing. So any individual 1 second measurement is not really meaningful. You need to average out this feedback cycle. And so all of these values refer to, well, what is that smoothing to filter out this feedback cycle? And the smoothing is done here in this particular profile, something like 3 seconds at the surface. 3 seconds equates to about 15 meters vertical resolution. To here, maybe 20 to 30 seconds. That's about 100 to 150 meter vertical resolution. So this uncertainty, 0.1 K, 0.2 K on frost point temperature refers to your vertical resolution, your average value within this 150 meter layer. But nevertheless, that is very good. Well, this is just one sample. Can we prove that this is actually true for all the soundings? And for that reason, in Lindenberg, we've done a number of dual soundings where we actually put 2 instruments on the balloon. And as I said, it's a very extensive operation, so that's non-trivial. We didn't do that just to test the reproducibility. We actually do this to test any changes we implement and what the impact is. But nevertheless, it allows us to compare 2 different instruments on the same balloon measuring the exact same thing. And so I calculate a tropospheric difference and I calculate a stratospheric difference between those. This is temperature difference, frost point temperature difference between those 2 instruments for 7 different dual soundings that we have so far. And you see for most of the part, they're within 1/10. Occasionally, there's the most extreme is 4/10 different here in the troposphere. Some of those are actually a result to those changes that we introduced. But on the whole, we're actually doing reasonably well. So it's that we can actually say, yes, we can reproduce those observations if we put 2 instruments on the same balloon. If I do calculate the same difference as mixing ratio difference, it's easier to think in mixing ratio difference percentage, we're within 2%, plus minus 2% mixing ratio difference. This is how well we can reproduce the measurement with two instruments on the same balloon. So that actually is very encouraging. If we look at trends of 10%, our uncertainty, our measurement is reproducible to 2%, we're probably doing okay. But I'm still worried about those outliers. Every once in a while, some of those where we had bigger differences. Well, is there a way that we can test this on the ground? So in Lindenberg, we introduced now a pre-launch ground check, where we actually test the instrument right before launch against a reference instrument. Can we identify the behavior of different instruments? And that, again, is non-trivial. It's actually quite complicated to do this, but I'm happy that we have a few results. And so we have a total of 8 where we did this. We just started that this year. And comparing to reference and reference and quote, I'll say something in just a second. We're typically within 0.2 of a Kelvin. And the reference instrument is nothing else than a polymer instrument, something like your Weissler HMP 45 or what have you. Except we recalibrate this one after the measurement. So it's a recalibrated polymer sensor, which has its own uncertainties. That uncertainty is included here. So that's actually the combined uncertainty of the frost point and this reference instrument. So seeing something like 0.2 of a degree scatter in this ground check is a very good thing. So we can definitely detect if an instrument was funny, if it did something really odd on the ground, if the calibration was odd on the ground. If I calculate the same measurement again into stratospheric mixing ratio, what would that be? So here it's 4%, 2, but most of them are plus minus 2% mixing ratio difference in the stratosphere. So to that level, we can actually test and qualify the instruments on the ground. The uncertainty of the reference measurement is included in there. So that measurement is not perfect either. So trends of 10%, 2% uncertainty. Now let's go to relative humidity. And here, of course, most important to me is relative humidity over ice, because we're at a really cold temperature range, and relative humidity right at the tropopause. That's where it really matters. But let me just show you here relative humidity from the CFH measurements, just plotted straight. Basically, you see a stratosphere is just bone dry, and there's a lot of variability in the troposphere. Nothing unusual. It's not that many soundings, but I can do a statistics nonetheless. I do something like a monthly mean. It's not a lot of soundings, but I just do it because I can. And this is what comes out. Yeah? Some intermediate RH. Here's your average tropopause, bone dry stratosphere. Well, if I want to look particularly at the tropopause, I shouldn't be doing it this way. I do it on my monthly mean on geometric geopotential altitude. But if I go back here, you see the tropopause is bouncing up and down. So I'm averaging sometimes stratospheric air, sometimes tropospheric air. So it's not a very instructive way of looking at it. I could go and shift all my profiles so that my tropopause is always at the mean tropopause level. So now I just shifted all my profiles vertically. Doing that, my tropopause, by definition, is now the mean tropopause. Now all the profiles are lined up right here. And now I see the tropopause is actually my cutoff for relative humidity. Now, I may have saturation all the way up here. Above that, immediately, boom, I go bone dry into the stratosphere. Nothing new here. I mean, this is not terribly surprising. But what I can do now, I can do, again, a climatological mean, okay? So it looks slightly different. I see here my constant, relatively moist upper troposphere. Keep in mind, there's only 140 soundings that we have in Lindenberg. It's not all that much. But I can also look at what is my RH distribution right at the tropopause. And so this is how it looks like. This is my frequency distribution. How often do I see which relative humidity over Lindenberg, right at the tropopause. So we do see occasionally some supersaturation. Supersaturation maybe in cloud, maybe not in cloud. We don't know from these observations. We just see air is supersaturated. There is some fraction that is exactly at ice saturation, but there's also a very long tail here. We even see really bone dry observations. That's how it looks like. If we only had a means to increase those observations, get more of them, we could improve this. And this is where gluon comes in. We actually do have that. And in Lindenberg, from our radiosondes, we have 4 times daily radiosondes. And we can use those radiosondes, especially in Lindenberg, to do the same climatology, so it's the exact same thing, except now I use the Weissler RS-92 processed with our gluon algorithms. And the catch here is that we remove all those known artifacts of the Weissler RS-92. There's solar radiation impact, there's a time lag, there's a calibration dry bias. All of those factors we correct for. There's a ground check issue. All of those we take out, so we make the best possible data set out of that. And by doing so, we go from 140 soundings to 7,000. Now we actually have a decent statistics to look at. And if I show you the RH distribution right here, oh, it actually looks kind of similar as the just from the CFH. So that is just a little taste of what you can do with the radiosonde if you push it as far as you can. But on average, of course, we're too dry. It's not a surprise. Lindenberg tropopause has nothing to do with stratospheric water vapor. It's simply too dry. This is what Brewer found with his measurements back in the 40s. So it's a lot more interesting if you go to the tropics, to Costa Rica. There we have soundings now since 2005, or coming up to almost 10 years. Here I plotted just the water vapor mixing ratio profiles straight as they come. Sorted by month, but irregardless of which year they were taken in. And just plotting them straight, you see one nice feature right here. And you see another feature right here. You see it much better if I plot the monthly means, so average all of those into monthly means. This is the tape recorder. Tape recorder, Phil Mode was the first one who published that back in '94, I guess, from Halo data. Here we see it now from in-situ observations. You have here drying in the northern hemispheric winter, January, February, March. This drying, this minimum, moves upward in time. And you actually see it again next year. And the same, this maximum here that forms in July, August, it moves upward in time right here. This is this upward branch of the Brewer-Dobson circulation, imprinted on the water vapor that crosses the tropical tropopause. So there we see the motion. There we actually can visually watch the Brewer-Dobson circulation. Well, of course, I want to know how much water goes in there, or what's the process right at the tropopause. Again, now I look at relative humidity, the same thing what I did in Lindenberg. And again, I just averaged, did monthly averages, and just kept all the profiles as they are. And yeah, that's what comes out. Up here at the tropopause, yeah, it's on average 75% RH. I'm not quite sure what it tells me. An interesting thing, what you see here, of course, is that big feature, and that big feature. Yeah. This is the climatology over Costa Rica. You have a strong rainy season right here, lots of convection, lots of rain, and you have this very dry season here, and actually it starts late in the year. If you come back to that earlier figure that I showed, yeah, that there are convective and non-convective regions in the tropics, this also is a function of season, and you see it right here. There is no convection ever here in January, February, March over Costa Rica. Always blue sky, well, maybe some low-level clouds. But very dry troposphere. The TTL, the tropopause layer, is nevertheless quite humid. Here you have this deep convection going on. And in fact, if you look very closely, you see that they have 2 seasons when the ITCC moves twice across. Here in June, and then again in October, and this year, August, September, they call this veranillo, the little summer, yeah, where the deep convection is not quite as intense as in the other 2 seasons. We started our TCSP soundings here in July in 2005. Of course, again, here, if you look at the tropopause, I just average over geopotential height, but it's not very instructive. It would be much better if, again, I lined up all my tropopauses. And that's what I do in this one, right here. So now I shift all profiles so that the tropopause lines up to the mean tropopause height. And look what comes out now. The color changes here, right at the tropopause. We have very high humidity, right at the tropopause, 95, 100%. Here, climatologically, you barely make it out. It's supersaturated, climatologically, over ice. And now I can do the same thing as I did in Lindenberg, just do my RH distribution right at the tropopause. This is where the dehydration happens, and here we can see it in action. This is now, compared to Lindenberg, and in red, the RH distribution at Costa Rica. The most common is ice saturation. So on average, the tropopause over Costa Rica is ice saturated. We have a nice tail to oversaturation, supersaturation, to almost 150% supersaturation over ice. Keep in the back of your heads, the uncertainty on those measurements is maybe 2, 3, if you include the temperature in there, maybe 5%. So here on this 150%, I give you 5% of those 150, so what, plus minus 7.5% uncertainty. This is very strongly supersaturated. We also have a tail here to subsaturation. Not surprisingly, every once in a while it's subsaturated, there's nothing happening. But the most common is ice saturation, and because that distribution is nearly symmetric, also the mean value is ice saturation. What that means, if you take the temperature, the mean temperature at Costa Rica, you can calculate what is the mean water vapor crossing the tropical tropopause at Costa Rica. Forget all about the ice, supersaturation, forget all of this. At Costa Rica, it works. And so if the entire tropics worked as we see in Costa Rica, then it would be very simple. You just calculate your mean tropopause temperature, calculate the water vapor saturation mixing ratio, and that's the water vapor that goes up into the stratosphere without ever having measured it. If that worked that way everywhere, it would be an easy job, and I probably wouldn't be standing here. So let's look at the Tibetan Plateau. The Tibetan Plateau gained some attention because from satellite measurements, we recognize that there is a strong maximum of water vapor in the northern hemispheric summer over the Tibetan Plateau. And so I'll show you, and I'll make it short. This is just the mean water vapor profile, and I already did this adjustment to the tropopause. I lined up all the tropopauses so that the mean tropopause of this particular data set. And you actually see here just a little bit left over of the tape recorder there. Well, it's probably more this is not true tape recorder because they're probably a little bit too far north to be in the ascending branch of the Brewer-Dobson circulation. But more interesting, of course, is the RH. Is that region responsible for dehydration at the tropopause? Again, this is the same thing. Here I've lined it up, all my tropopauses, and you see here on average it looks like more in this range, 75. And if I do my RH distribution, you see here in this orange curve, this is what it is. You have, same as in Lindenberg, some observations that are supersaturated. There is a small peak here right at ice saturation, but there's another bump here at 75 and a very long tail all the way down to 20. You already see it. The mean value of this one is, I don't know, 75, 80%. This is not, on average, saturated. So if you wanted to take the Tibetan Plateau or this region and calculate your water vapor going into the stratosphere from the temperature, it wouldn't work. That also means that this air that we observed here is drier than saturation, which means it was dried out somewhere else. And we have to find, where is this somewhere else? Where does that air come from? So let me go back here to this earlier picture, the Brewer-Dobson circulation. Lindenberg, Boulder, they're here in this region, and we see actually very similar, very consistent trends. Because Lindenberg is a little bit closer here to this large-scale subsidence region, we see the polar vortex every once in a while, especially at the higher altitudes. It's interesting enough here. Jim Holton already put this little bump here indicating that at a lower temperature, at the lower altitudes, this region extends a little further northward. At a higher altitude, probably not, which might explain why we have better agreement between Boulder and Lindenberg at lower altitudes than at higher altitudes. Hilo is also somewhere right in here. Costa Rica is the only site in there that we have. So what would be nice, if you actually could fill this picture that way. So this is latitudinal, and this is somewhat longitudinal. But it turns out what we have right now here, I put the balloon soundings, so the stations that we have our two polar sites, which I didn't show much about. If you Boulder, Lindenberg, I didn't say much about Lauder as well. So we have one southern hemispheric site. And we only have one site, Costa Rica in the tropics. What we do need is some other sites that capture this variation across the longitudinal little circle in the tropics where it really matters. So with this, I come to an end. In-situ observations provide high resolution and low uncertainty observations of water vapor in the upper troposphere and the stratosphere. 2 times monthly observations are sufficient for long-term monitoring here in Boulder because they're not that close to the polar vortex. It's probably okay with just once monthly, but that's really pushing it. Improvements in instrumentation reduce the uncertainties to definitely less than 5% in mixing ratio. So we actually have good confidence in these observations today. And then what I showed you with this additional ground check is important because changes in operational procedures, i.e. ground check, allow a better quality control of the observations. Recent trends of stratospheric water vapor at several stations are consistent with each other. So far for the trends here for dehydration, the mean tropopause RH over ice at Costa Rica is near 100%. That means the tropopause temperature is on average a good proxy for water vapor. The mean tropopause RH over ice in the Tibetan Plateau is less than 100%. This is not a good proxy for water vapor. Yeah? So what we do need is year-round soundings in the Western Pacific. I didn't say much about that. It's the old stratospheric fountain hypothesis, which is the Western Pacific. It would be nice to have simultaneous in-situ cloud observations, especially in Costa Rica. And I actually put this just as a bullet because I cut out this entire section. We have now the capability to do these observations. We have an instrument in Lindenberg, we're actually flying it. So we can do this study also detecting whether we're in cloud or not. We need more in-situ observations in the Indian monsoon region, which I suspect is actually the region where this dry air comes from that we see over the Tibetan Plateau. And it would be nice to have some routine observations over the Atlantic and the African region, which is a complete black hole right now. And with this, I end. Thank you.
Questions for Holger?
When you talk about accuracy of the measurement in stratosphere, and for your test, you can average whatever you want. But in measurement, how fast the balloon rises, and what's your average time for real observation?
That's a very good point. Let me see. That's this one. Let's see how fast is this way, maybe. Yeah, come on. Should have brought the power supply, sorry. There it goes. 1 second. This is the answer to your question. So vertical averaging, really we need to do vertical averaging a little bit, and the averaging time, vertical smoothing that you need on your data is dependent on temperature or altitude. And so we start typically with 2 to 3 seconds averaging near the surface, and then maybe 20 to 30 seconds in the stratosphere. Seconds times the ascent speed, and a typical balloon rise rate speed is 5 meters per second. So times 30 seconds is 150 meter vertical averaging. Nevertheless, we have 1 second resolution data, but there has to be something like this 30-second running mean filter over that one. So that comes out about 150 meter averaging. Does it answer your question?
Yeah, because I was wondering why the different average time with the
Yeah, and that's simply specifics to the instrument. At the surface, there's much more water vapor, so this feedback cycle can run much faster. When you're at 5 ppm, that feedback loop automatically becomes slower, so you need more time to average those controllers features out.
The balloon also goes slower as you go higher.
A little bit, yes.
So, Holger, I very much agree with you. I think we should do more in Western Pacific. I saw on your map there are dots in Manus Island and Nauru. What happened? Did it, not in a routine basis, did we ever had some sounding in those locations?
Yes, that's a very good, very, very good question. I'm actually very upset at ARM about this particular because I had long-term plans to start this sort of observations at Manus. And last year they announced that they closed the site. So Nauru was closed last year. Manus is going to, maybe Manus is closed already. And Darwin as ARM operation is going to stop at the end of the year. So those sites are going to go away. So we will not have the chance to use the ARM sites for these observations. No, we were never able to get that. ARM, they got started on CFH measurements this year. In fact, they'll be doing the next sounding next week at SGP. And the original plan was once they know how to do the SGP, they can do it at the tropical Western Pacific, but voila, they closed the site. We're really hopeful that we can maintain Darwin. Darwin as a sounding site is actually a BOM, a Bureau of Meteorology. So the soundings are run by the Australians. And we're working hard to get them into Gruon and maintain at least the Darwin site with the hope that maybe we can get frost point soundings from there.
There's?
So the frost point measurement basically depend on the physical principle of temperature and saturation or freezing relationship. At this kind of extreme low temperature, how well do we know the physics of equilibrium conditions of that freezing, how fast it happened, how, that's really down to the extreme low temperature part of it. How do you have any?
It's the dynamics is not that important because the instrument tries to maintain a constant frost layer. So when you see evaporation or condensation, the instrument automatically counteracts that. And this frost layer is stable to what, 0.2%, something like that. So it's really stable. So the variation around that equilibrium is very small. That's what makes it so very sensitive. So the key question is, how well do we know the vapor pressure equation? That's the ultimate one. And over ice, it's a lot easier. There's some lab measurements back in the 90s, early 90s. So we definitely know it to within 2%. No.
That curve essentially shows the time factor, like how fast we reach that or something like that.
This is how fast the feedback loop is running, or how much time you need to average out your feedback loop reasonably. And this is actually done profile by profile. This is not a mean thing. You can really do this profile by profile.
Actually, while you're talking about instrumentation, are you happy with the cryogenic frost point hygrometer, or are there other technologies that you'd be interested in exploring for high altitude water?
Right now, this is the only one that exists that can do that operationally. There are a few there's a few other technologies. One is a Russian group. They've built a Lyman alpha instrument, also relatively small. And in fact, we have done a few comparisons with them. The nice thing is, nice for us, for me, the agreement with the CFH is actually very good, to within, I don't know, a few percent. The problem with that instrument, each one has to be calibrated in the lab against water vapor. So you need to have a very good water vapor calibration system. The CFH is calibrated against temperature, which is a lot easier. So that's the one thing. And the second one, it's very tricky to maintain the calibration into the field because you chip the instrument, make sure your optics is clean and all this. So there's some small issues with that. Plus, it's operational and non-trivial and even more expensive than the CFH. So that's the only other balloon-borne technique, small balloon-borne technique out there right now. Vaisala is working on what they call their reference radiosonde. They actually have a polymer sensor that works in the stratosphere. And we've done in Lindenberg, we've done a few comparisons with them. To my big surprise, that instrument is sensitive to water vapor in the stratosphere. Seeing a polymer sensor being sensitive to water vapor in the stratosphere is extremely remarkable. However, they have a big problem with the calibration. So they're within, I don't know, 20, 30, 40% of the CFH, which means they see exactly the same structure as the CFH, but maybe offset by a ppm And then it's no good, yeah, because we're looking at these 2-3% changes, and if you're not sure about the calibration, then it's not good. But that's in development, so I have no idea how far they can push it. And basically, that's all I know for small balloons. You can go on big balloons, you can go on research aircraft, and you have TDL and Lyman alpha technologies available. But on the small balloons, that's it.
No.
For a flux, you need humidity and vertical motion. And I'm wondering if there is a correlation that might introduce a bias. I would expect the high supersaturation events to be moving up faster and therefore contributing more to the flux than the low supersaturation events. Do you have any feel for how this correlates with vertical motion?
No, not at all. And we do not have any measurements of vertical motion in this layer. And I always had a hope that we can do it from the balloon rise rate itself. But it looks like we probably can't. Yeah? In the troposphere, it may work. Jun Wang and Jianjun Bian, actually, one of the co-authors here, they worked out that you can derive or get an estimate for vertical ascent speed by comparing your measured vertical ascent, balloon ascent, compared to the expected balloon ascent rate. And the difference would be the air motion. In the troposphere over larger layers, that probably works. Right at the tropopause, there are a lot of funny things happening. And funny things meaning a balloon speeding up from 5 meters to 15 meters per second, which is unphysical. I mean, it's not happening in the air. It's not going up to 15 meters per second across the tropopause. And then you look into the dynamics of a balloon and you realize, oh, it's in this Reynolds range where you may have turbulent flow transitioning to laminar flow around the balloon, plus the physics of the balloon material itself changes also. And so all of these factors in there, so it's not possible really. So we don't have any vertical motions information.
If there aren't any others, I think we'll thank Holger again. I should point out I have seen some people I don't recognize. We try to keep track in EOL of visitors that have come, and there's a sign-up sheet by the water. So if you could just scribble your name on, that'd be great. Thank you.